Okay guys, so we are cruising and we are making a bit of progress. So this is another series of videos with regards to introduction to IT. It's a second year engineering course at the University of Zambia, but if you're at any other university and you find this obvious, you can be sure to check it out. So this video is basically a continuation of the previous video, in which we introduced chapter 1 and also looked at some basic themes such as computer architecture and the likes. So if you haven't checked out that video, be sure to first and foremost start with that video before you begin this video series. Yeah, so in this video specifically, our main focus is CPU registers. Yeah, because if you recall, the previous video ended with us highlighting the fact that CPU registers are one of the components found inside of CPU. Yeah, and we did give out two special purpose registers which are required of us to know. Yeah, but then another thing which is of importance to us is something which is known as CPU system buses. Yeah, so this is basically what it is called. So now for us to understand CPU registers, we first and foremost need to look at what a bus is. So how would you describe or define a bus? So a system bus is a set of electrical paths that connect major components of the computer, such as storage and input/output devices. Yeah, so basically this is what a CPU system bus is. So now for the purpose of this particular course, we find the need to look at three important CPU buses. So number one, we need to understand what an address bus is, and then secondly, we need to understand what a data bus is, and then lastly, we need to look at what a control bus is. So these are the main three CPU system buses that we find useful to us in this particular course. So now, starting off, first and foremost, we need to understand what an address bus is. So like I've said, CPU buses, basically these are a set of electrical paths that connect major components of the computer. So basically these are like the link which enable transferring of information between computer systems. Yes, so when you look at an address bus, what this does is that it carries memory address from the processor. This is very much important. It carries from the processor to other components such as primary storage and input stroke output devices. Yeah, so this one carries from the processor and it goes to other components, any other component, but it's coming from where? From the CPU processor. So one thing you guys need to note about an address bus is the fact that it is unidirectional. So you can just say the address bus is unidirectional. Yeah, so in other words, we can say maybe it only goes in one direction, which is from the processor to other components. Yeah, so moving on, we also want to know what a data bus is. So when we look at a data bus, it also carries something, but then what is that something? So we can say it carries data between, this is very much important, between the processor and other components but because we've used the word between, we should be able to have an idea to say it can go back and forth. Yes, so unlike the address bus, we can say the data bus is bi-directional. It can go in both directions. Yeah, bi-directional, because we've even used the word between. So that's the main difference between an address bus and a data bus. Remember, a data bus only carries from the CPU and it takes to the component where it is required, and what it's carrying is the memory address and it's coming from the processor. But the data bus can carry data in general between both the processor and any other component. So but then what about a control bus? So when we look at a control bus, this one carries control signals from the processor to the other components. Yeah, so but because whenever we mention to say from the processor to other components, what it's carrying is what? Control signals. This means that a control bus is unidirectional. It can only move from the processor to that other component and not the other way around. Yeah, so this is what we mean basically by that. Yeah, so now that we have understood what buses are, so one thing I would like to make mention of is the fact that my videos are basically going to focus more on concept understanding. So if you guys want to have a clear representation or to see some visuals of how these things look like, be sure to look them up on Google. I don't know if I mentioned that, but yeah. So now that you have understood the concept, so for an address bus, it's carrying memory address from the processor to any other component. Then for a data bus, it's carrying data between, back and forth, between the processor and any other component. For that reason, it is bi-directional. And when we look at the control bus, it carries control signals from the processor to the other components. Yeah, and it is unidirectional because if it can only move in one direction, then we say it is unidirectional. So now let's move on and progress, because remember this video is focused on CPU registers, because the rest of the video will be trying to understand what CPU registers are. Yeah, so CPU registers are one of the components which you find inside the CPU. Remember, in the previous video we looked at the other components which are found in the CPU, but because CPU registers are of great importance to us in this particular course, we have decided to make a separate video just for them. CPU registers, this is how important they are. But the other components, we managed to fix them in the first video we made. Yeah, so without wasting much of the time, let's try to understand what CPU registers are. So the main role of registers is simple. So basically, as the CPU is running arithmetic operations using the ALU, you notice that registers store temporal chunks of data. Yeah, so in other words, registers are more like storage locations in the CPU. So remember, we did talk about cache memory and all that, but unlike cache, which basically is a nearby memory which is used for storing data which is frequently accessed by the CPU, registers, they are mostly involved in storing temporal chunks of data as the CPU is running arithmetic operations. So that's the definition. So the role of registers is as the CPU is running arithmetic operations using ALU. What do registers do? Registers store temporal chunks of data. Yeah, so a common example of registers is special registers. Yeah, so we have what are called special registers, and this is of our main interest for this particular course. So when we look at special registers, for the purpose of this course, we just pick 2 of them, but then we might need a few more to understand the example which we are going to give later on in the video. It will summarize everything about registers. Yeah, so but the ones which you are supposed to know like the back of your hand are the program counter, also known as the instruction pointer, and at the same time you also need to know the stack pointer. Yeah, so now since we need to know them, let us just know them. Okay, so starting off, number 1, program counter, also known as instruction pointer. Yes, now when we look at the program counter, our main focus is maybe to try and know where it got its nickname from. Instruction pointer. Why do they nickname it as instruction pointer? Because its real name is program counter. Okay, so now when we look at the program counter, the best way to describe it or define it is by saying this is a processor special register. Then we know that registers basically they are used for storing data, and this is usually as the CPU is running arithmetic operations. So we need to know the content which is found in a program counter, since we know that it stores data. So but for the program counter, it is a processor special register now whose content is the memory address of the next instruction. This becomes important in anything we say about a program counter. Next instruction, it is always going to be pointing toward the next instruction. Yeah, and you see this in the brief example we're going to look at the end of the video. Yeah, but basically this is what a program counter is. So now moving on, we need to also know what we mean by stack pointer. Stack pointer. So, but because we're introducing the word stack to most of you for the first time, it is going to be important for us to understand what this word means. Stack. Yeah, not stack as in your stack trying to understand maybe what trigonometry is, but stack with an A. So now stack is a very important concept when we talk about computers in general. So basically first let's try to understand what a stack pointer is, then we'll explain what stack is. So just like the program counter, the stack pointer is a processor special register whose content is what now? Whose content is the last request. The last request. The last request on stack. But then remember, we cannot understand the stack pointer without even knowing what stack is. So now we need to know what is stack. Yeah. So when we look at stack, we're not going to go in details trying to understand how it functions and all that, because remember, this is just an introductory course to computers. It is not preparing you to become a computer scientist or anything like that. So let's just look at a brief picture. Picture this is the RAM. So basically, stack is a region of memory inside of the RAM. That's all. That's what stack is. It's a region of memory inside of the RAM. But then this stack, basically, what you need to know is that inside the RAM, inside the RAM, the CPU allocates and reserves a certain memory, a certain memory called stack. Yeah, that's what stack is. So as the CPU is running, it's going to allocate a certain region of memory called stack. But then that's not enough for us to understand stack. So stack memory, basically, what we can say about it is it is a special type of temporal memory inside of the RAM for data storage during program execution. So we can say stack memory is a special type of temporal, remember, temporal memory in the RAM for data storage during program execution. During program execution. And we understand this better, the concept of program execution, in the example which we're going to look at the end of the video. But then remember, I previously said understanding the fact that stack is the region of memory inside of the RAM is not enough. We need to know how stack works. So one of the most important concepts or ideologies about stack is but the fact that it operates on LIFO. So what LIFO means basically is last in, first out. Yeah, so for you to understand what stack is, you need to know that it operates on LIFO, last in, first out. So for you to understand this analogy, last in, first out, let's look at an example of a queue. So this is a queue. Then we're trying to compare it to stack, which operates on LIFO. So each one of us, we've been in a queue before. So an example which I'm going to use is the queue of where maybe you are at ShopRite. You're going to buy some bread, but then that cheap bread, the one for, is it 10 kwacha, is normally on demand. So you find some people lined up to get that bread in a queue. So these are people who are going to get some bread on the counter. This is the first person, the second person, the third person, and so on. It can be the fourth person here. Yeah, so these people are lined up to get bread. This is the first, the second, third, and the fourth person. Just for educational purpose. Nothing fancy here. So basically this is how a queue works, and it's called a queue because once the bread is ready, this guy in front will start by attending to the first person in the line to say, get your bread, go. This person will go, and the second person will go, third, until the queue is done. So one thing about queue is you cannot cut the queue, because imagine this person just comes in, no, I'm a minister, so I need to be the first one to get the bread, and he tries to cut the queue. These people are going to be upset. You can't cut the queue. So this is what a queue is. But then when we look at stack, for us to understand how stack operates, let's look at an example of this same bread. Imagine you go home now. So you can think of it as maybe it is sliced bread. So when putting in the plastic bag, they start by putting the first slice, the second slice, until this plastic is full with slices of bread, right? So imagine now this plastic was closed. So you, when you buy that bread, what you're going to first and foremost want to do is you open it. Okay, you open the plastic. You want to start eating. The first slice of bread you're going to get is the one on top here. This bread here will be the first slice you get. And then you go all the way, going down up until you reach this last bread. But then the difference between stack and queue is in a queue, this person in front was the first person to arrive there. This is the reason why they'll be attended to first. But when you look at this, this plastic bag of bread, the first slice of bread which was put is the one which is down here. But then at the same time, it's going to be the last bread to be removed from this plastic bag. So with that idea comes in the concept of last in, first out. So the first request which is going to be entered on stack is going to be the last to be attended to. But then the one which is going to be attended to first is the last request you made. So this is a basic idea of how stack works and why they say it works on the concept of LIFO. So you can picture a plastic bag of bread. Then when you are putting slices of bread, because you need to start with this slice, then this, until you reach the last slice. But then when you are eating, you remove the one on top, which was the last to be put in the plastic bag, which is different from a queue. Because in a queue, the first person that arrived there, if you go there at 05, you'll be the first person to be attended to, and you automatically leave. So that's the basic idea between stack and queue. So we're saying stack memory operates on the concept of LIFO, and we've now understood what LIFO means. But before we look at the example we want to look at, which is going to end this tutorial video, let's go back a bit to program counter, because it is much more important for us to discuss it a bit more in detail before we look at the example. Yeah, so when you look at the program counter, it's referred to by many other names in most mainstream books. So it's also known as the instruction pointer. And we'll know and understand this in a brief. Instruction pointer. It is also known as instruction sequencer. Instruction what? Sequencer. And it is also known as instruction address register. Instruction address what? Register. This is what a program counter can also be referred to in some other books. So if you are reading a text and you find that the written instruction pointer, just know that they are talking about program counter. If you say you are reading a book, you find the written as instruction sequencer, just know that they're talking about program counter. And at the same time, if you are reading a book, you find the written, sometimes it can be used these initials IAR, just know that they're talking about program counter. So that's what program counter can also be known as. So now our next subheading is to understand how it works. How does program counter work? Program counter work. But because remember, we have said program counter is somehow of importance to us. It is going to be of great importance for us to understand how it works. So it is not possible to explain how a program counter works just by looking at the program counter itself. We need to bring on board many other ideas. This is why we started by looking at a bus and all those things. But remember, it was very easy for us to understand how a stack pointer works. All we need to know is the fact that stack is a region of memory in the RAM, which is allocated by the CPU during program execution. And at the same time, we need to know that stack operates on LIFO. And we're good. We've understood how a stack pointer works. But program counter it is much more difficult to understand it. And basically, it may be the last thing we're looking at in this particular video. So the only way we can understand program counter is by looking at an example. This is why we said we look at an example, and some of the things will become clearer. Yeah. So let's move on with our example. So I shall call this example the fetch, decode, execute cycle. The fetch, decode, execute cycle. This is going to be a very long example. It's a classical scenario of trying to understand how a program counter works. But we've decided to bring on board all these ideas because that is how complicated it is for us to understand how a program counter works. So without wasting much of the time, let's get right into it. So you need to consider in your mind this piece of code. This is a high level language code. Yeah. So, but then again, remember we said the first part of the course is mostly about the hardware of the computer. The second part is the one which is going to delve more in terms of programming. But then for the purpose of understanding this idea about program counter, we decided to bring on board some concepts about programming. But nevertheless, even if you don't know programming, I'll try and explain every term as we go on. So what we mean by a high level language code is basically as you become a programmer, that's if you want to venture into that field, you realize that assembly, not necessarily assembly, when you talk about languages, you're going to notice that the languages which you find in programming, they can either be high level or low level. And what this simply means is that when we say high, it means it is much closer to the understanding of humans than it is to the understanding of computers. Because remember, computers do not understand human language, but what they speak is binary language. This is something you need to understand. So computers understand binary language and not human language. So when we say high level language, it is a piece of code basically which has been written in such a way that just by looking at it you can make sense of it, say okay, this makes sense, and it can do something for you at the end of the day. So the code we're talking about is this code: z is equals to x plus y. So how this works, if let's say for instance you're talking about a language which uses a compiler or an interpreter, no one really cares, but then what it's going to do is take x, and to that x add y to it, and then get the result and store it in a variable called z. Yeah, I know it sounds a bit fancy, especially if you're not much into programming, but then it's just for the purpose of this example. Take x, add y, and the result of that, store it in the variable called z. This makes sense because like I've said, it's a high level language code. It's been written in such a way that you can look at it and make sense of it. But then let's move on to look at how an assembly language source code would look like. So basically, an assembly language source code, what we mean by that is it's been written in a low level language. And what that means is the manner in which it's been written, it's much more closer to the understanding of computer language than human language. What this means is a computer can easily make sense of an assembly language source code than a human being. Because as a human, you can look at an assembly language source code and be like, what's this? But a computer, it will look at an assembly language source code and be like, aha, this is what I want. Yeah, so for the purpose of this example, consider this. Load 10 and then add 11 and then store 12. This is a classical example of an assembly language source code. As a human being, even some programmers, okay, not a programmer, okay, as a human being, because a programmer would know what this means. They will look at it and be like, what does this mean? Load 10, add 11, store 12. But I'm here to tell you, this example is going to try and explain to you what this code means and how registers come into play, particularly program counter and some other which we may find need to explain this example. Yeah, so for us to understand this particular example, you need to know that there is need to think about the accumulator. The accumulator. So aside from the arithmetic logic unit, which is a component found inside of the CPU, there is also need for us to look at what the accumulator is. But no need to worry about the accumulator because it is just another component found in the CPU. So yes, so there are a lot of other components which we didn't really mention in the previous video we looked at, and an accumulator is one of them. So let's try to now understand what we mean here. So when you look at this particular source code here, load 10, add 11, store 12. So what this means is that load the content stored in memory location 10. This 10 is the memory location. And then what you're going to do is load this in the accumulator, right? And then at the same time, add the content of memory location 11, because this 11 is a memory location to what is already in the accumulator. So you can think of it as an accumulator is more like a shopping basket. So you load the content of memory location 10. So memory location 10 is more like a room. You can call it 10. There's something in this room 10. So what we want is we want to open this room. We open the door, then we see what's inside of 10, then we put it in the accumulator to be here, whatever is in here. Then at the same time, we also go to the memory location 11, and then we're going to add to the accumulator what is inside of this memory location. So we're going to have something else here which was in memory location 11. Then now we'll pick this up, then we'll store it in a different memory location which is called 12. You can think of it as a room with a number 12. So basically this is what this means. So now like I said, we're just trying to understand the concept of program counter. We are not preparing you to become a computer scientist, and it makes sense even if you don't understand it at first glance, but all you need to do at this point is have an idea. So one thing I would like to make mention to you guys is, remember, I'm referring to the memory addresses of whatever it is we're talking about, the contents by numbers 10, 11, 12. So this type of memory addressing is referred to as direct addressing. So it's something you ought to just know. Referencing to memory addresses using numbers is called direct addressing. Yeah, so this is what we mean. But then aside from direct addressing, we also have another form of memory addressing, which is known as symbolic addressing. So this is just a takeaway if you want to know more about this. Yeah, so we can also have symbolic addressing. So remember, even though we are saying when we talk about an assembly language source code, we're saying it's much closer to the computer than it is to the human beings, but still the computer has an idea more than you, but it still can't completely understand what you're talking about. So even after that, the assembly language source code has to be turned into machine code. Yeah, so instead of us having an assembly language source code, it needs to be turned into machine code, and we know that the computer understands binary language, which is a series of zeros and ones. So that's what we mean by that. So maybe just a quick example. So consider the scenario which happens in a 16-bit machine. So this is a very old machine, because when you go on the market, the most common machines which you find there are 64 bits, maybe sometimes 32 bits machine. But a 16-bit machine is okay for us to understand the next example. So you can consider this example where you have this piece of code, then it can be, so this is the operation code, and at the same time this is the operand address. Yeah, so basically this will be the operation code, which is going to be converted to the operand address as yeah, so as you can see, this is 16 bits. Yeah, this would be 6 bits. Yeah, but this was just an example of how it would look like in a 16-bit machine, where the operation code is converted into an operand address like that. So but then remember, I said this is just an example for you guys to try and understand how a program counter works. It's not necessarily important that you should understand or memorize some of these concepts, but it will help you understand a program counter better. That's how complicated it is. But then this is just an example. You don't necessarily have to fully memorize and understand it, but all you have to do is have an idea. So now our main focus here is looking at this schematic here. Yeah, so this is how the whole picture would look like. So yeah, I've just roughly drawn it up so that you guys can have an idea now. So remember, the example is called the fetch, decode, execute cycle. Yeah, so meaning there are 3 main steps involved in this example: fetching, decoding, and executing. And it's called a cycle because it repeats itself over and over again. So our main example is but the earlier example we had looked at of an assembly source code, because this one is much easy to understand, but then what we want is this other one here. So it says load 10, add 11, store 12. So basically what we are saying is we need to put the accumulator into perspective, which is given the fact that you are going to load the content of memory address 10, then you're going to store it in the accumulator, and then you're going to add to that what is in the memory address 10. You add what is now in the memory address 11 into the same accumulator, then you store the results into a different memory location called 12. But then we're trying to understand how this works by looking at a schematic diagram of the CPU. So basically this is how the diagram would look like. These are the registers here. So as you can see, we have the program counter, which is the one we're trying to explain, but we have to explain the program counter by going through all this struggle here, because it's the only way we can understand it and how it works. So it's like we're getting just a small component of the CPU and we're trying to understand it, but unfortunately it's not that easy to just understand it on its own, because it works in collaboration with these others. Yeah, so this is why we're trying to look at this example here. So another register which we have found used to mention is the current instruction register, the memory address register, and the memory data register. But then the most important one is the program counter, because it's the one we're trying to understand. Then on this side we have the control unit, the arithmetic logic unit, and the accumulator. So you find that in mainstream books, the accumulator is going to be part of the arithmetic logic unit, because I think it's a component found inside of the arithmetic logic unit. But either ways, we've just decided to join it outside so that you guys can see what's happening here. And this is the control bus. And remember, we started by looking at CPU system buses, and we've already said a control bus is basically one of the CPU system buses. We also looked at its use. Yeah, and then in this region now we have the content which we are looking at. So you can think of it as the same way I gave you rooms. So these are like rooms, and then you can think of it as a room which has a number on the door. So that number is the memory address. So for instance, if someone tells you to say, let's say you are 2, that is your name is 2, because that is what you are. So you are the content which stays in that room. So where do you stay? You stay in room 10. That's your location. So I don't know if that makes sense to you guys, but this is what we mean. This is the content and where it is found, the location. So I said if we're using numbers to address memory locations, it is called direct addressing. Yeah, so this is what we're doing here. This is the memory location and this is the content 0 0 0. Yeah, so now we're just trying to see how the program counter comes into play. And then here we have left a gap. It changes, it's not necessarily the content but the instructions, but still the right hand side is the memory address of that instruction. So it's like you have a certain instruction and it is stored somewhere in a specific location. Then remember, we're talking about the RAM in this case. So these memory addresses are locations found in the RAM. Yeah. So yeah, now we want to understand our example, which is load 10, add 11, and store 12. So now, how does it first and foremost come into play? So before we can say anything, remember the name of our example is fetch, decode, execute cycle. So the first step is fetch. But then before we can even fetch the instruction from the RAM, so you can imagine the RAM is not part of the CPU, it's outside of the CPU. This is why in my diagram I haven't drawn it here. But maybe you can say there's a RAM somewhere, I don't know, somewhere. yeah, but it's not part of the CPU. So it's like we're fetching information because the RAM is the main memory for the CPU, which it uses for storing information. This is why we had to start and foremost look at the RAM and explain it. So now, before we can fetch, so fetching is more like getting information from the RAM. Before we can fetch the instruction from the RAM, that memory address needs to be placed into the memory address register. Yeah, so the memory address register will store the content before we even fetch that instruction. So like I said, down here is the instruction, then on top there it's the content. So what's the first instruction you requested for? You said load 10, but then we're saying what is going to be placed in the memory address before we even fetch is the address before we can begin doing anything. So you find that the memory address of load 10 is 100. Just like I said, you can picture it as a room where there are these instructions or whatever, and the room number is 100. So this is going to be stored here. So it's going to display 100 here. Yeah, so now once this happens, the content of that memory address can be loaded into the memory data register. Now this is what we call fetching now. So the content which is found in address number 100 is what? Load 10. So now this is going to be loaded into the memory data register. So you find that in the memory data register, what is going to display is load 10. So this is how the sequence works, and this is basically the step we call fetching of data. So now once the instruction has been fetched, because fetching is now placing it in the memory data register. So once the instruction has been fetched, it now needs to be placed in the current instruction register. So current instruction. So by the way, one thing we forgot to mention was the first thing first is the program counter is going to be pointing to that same instruction which we were supposed, the memory address of that same instruction, which was 100. So now once the instruction has been fetched, we are saying the content is going to now be stored in the current instruction register, which is load 10. So immediately it is stored in the current instruction register, you'll find that the program counter is going to be incremented by 1. So what that means is the program counter is going to be incremented by 1. So from 100 you're going to go to 101. And what this means is that this will enable the program counter to be pointing towards the next instruction, the memory address of the next instruction which is supposed to be fetched. So you notice that the next instruction in this list is supposed to be add 11, right? Yeah, so this is the first stage, which is all about fetch. So you notice that one thing you guys need to take away from is the program counter is incremented even before you can start working with the current instruction, before you can execute that instruction, which is loading 10, because we haven't loaded 10 into the accumulated, but the program counter has been incremented. Because in the case of anything you discontinue the process, the program counter always has to be pointing to the next instruction to be fetched, and specifically the memory address of the next instruction to be fetched, because remember that is what we said a program counter is. But this example is helping us to understand program counter even better. So before we can even go to the next step, which is executing or decoding, specifically executing, the program counter has been incremented and it's pointing to the next instruction. So the next stage basically is decoding in the sequence of fetch decode instructions. So decoding, basically what happens is the content that is stored in the current instruction, this is why it's called current instruction register, is now passed on to the control unit, and the control unit will try to make sense of it, and okay, this is what it means, load 10. Then it will try to, because we said the control unit is the one which acts like a traffic controller. It's the one which is doing most of the the processing. So it will process the data and say load 10. Okay, this is what load 10 means. Yeah, and it will be able to make sense of it. We're not going to go into details into that, but we just want to have an idea to say it will make sense of it. Then afterwards, the last stage comes into play, which is by far the most important one, executing. So in the process of now executing, which is loading now 10 into the accumulator. So at this point now, we need to make sense of what this means when we say load 10. So in other words, what we're trying to say is load the memory address 10. The memory address 10 is what? This one here. Load the memory address 10. So in other words, it's like we're going to fetch something which is stored in the memory address 10, because remember this was just an instruction and the instruction was stored in memory address 100. We've seen how it has moved starting from the memory address register where the program counter was pointing to it, and then it went to the memory data register, and finally to the current instruction register. So now in the process of executing, we are now going to have to fetch something again. So it's like we're doing the process over again. So it's like we're going to fetch something from this memory address 10. And what is that something? It is just a 2. I don't know if that makes sense. So again, not that the process repeats itself, but we're still in the first cycle, but then now we're just fetching that content now. So it's like this memory address, it needs to come in the memory address register, because remember that's the first thing which needs to happen. So you notice that the memory address register will change. It will now be storing this address which is 10. Make sense? And then immediately the memory address register stores the address of the instruction you're about to start performing. What's going to happen is the memory data register will store now the content you're talking about, or the instruction. So in this case it is just a 2. So this is what is going to be in the memory data register. You will have a 2. So this particular process is called overwriting. It's like there was something in the memory data register, but we have overwritten it. Then now we have a 2 being stored there. Then now after this content now is stored in the current instruction register. So now remember, something needs to move from the current instruction register, and then now it can be stored in the accumulator. So at that point you're going to notice that in the current instruction register it's going to change. You have your 2 there, then now your 2 can move to the control unit, then it goes in the accumulator. So this is how it flows. It will move to the control unit, then through the control bus and into the accumulator. So you find that in the accumulator now you're going to have what? A 2. So that is the first instruction now has been fetched, decoded, and executed. So the next instruction which is there, and remember the program counter at this point is already pointing to that next instruction, which is add 11. Make sense? So add 11 is stored in memory address 101, and remember program counter, that is where it is pointing. So it's like we need to repeat the cycle again for the next instruction. So the next instruction is add 11, but then it is stored where? In memory address 101, and the program counter is already pointing to that. So the first thing is that memory address needs to be stored in the memory address register. So it's like we can just copy this memory address from the program counter, then store it in the memory address register. Then we'll have 101. And then from there now, the content of that memory address, which is in this case an instruction add 11, is going to be stored in the memory data register. So in here we're going to have add 11 like this. Then immediately that happens, this is now passed on to the current instruction register. So in the current instruction register, you are going to have this add 11. Immediately that happens, by now you should be seeing what is going to happen, which is the program counter is going to be incremented to be pointing where? To the next instruction. Right before you can even decode or execute that operation or instruction, program counter needs to be pointing to the next instruction. That's just its job. Points to the next instruction. Specifically, it is pointing to the memory address of the next instruction to be fetched. Hence the title of the example, fetch, decode, execute. So before we can decode and execute, program counter needs to be incremented, and then the next instruction is going to be stored in memory address 102. So the program counter will change to now be pointing to memory address 102. This is how program counter comes into play. So immediately that happens, again, you will notice that the content of the instruction which is stored in the current instruction register is passed to the control unit. It moves like this via a bus. Then from there, the control unit will make sense of it, and then it will work with it like that. So now that is what is going to be called decoding. So it's like we have decoded the second instruction once we have passed it to the control unit, and the control unit has been able to make sense of it. Yeah. So this instruction says add the content of memory location 11 to whatever is already in the accumulator. Because remember, add 11, this 11 means add what is in memory location 11 to what is in the accumulator. Because remember, that's what I said in the beginning, to say add 11. But this 11 is not a number, it's the memory address of the content which is in 11. 11 is here, and what does it have? It has a 3. So now, in terms of adding, you can think of arithmetic logic operation, which is the ALU. So this is where now the ALU comes into play. So an add instruction is going to be passed to the ALU. So the ALU is going to be prepared to say, oh, I'm going to be adding something. It's like it's even going to be waiting to start adding something. So what's going to be happening is the content that is stored in the accumulator is going to be passed to what? To the arithmetic logic unit, which is the 2, right? So now after that, we can now get what is in the memory address 11. Remember, 11 is here, which is just a 3. But to get something is what we are calling fetching. So the same process needs to happen whenever we're getting something, because remember, the memory locations of this thing are stored in the RAM. So it's like there's a process which we follow when getting something from the RAM, and then we want to put it in the CPU. So that is the same process: fetch, decode, execute, cycle. So it's like we're going to fetch something from what? From memory address 11. So the same thing is going to happen. You find that the memory address register is going to have the memory location of that content 3. So what's the memory location? 11. So you notice that in the memory address register, you're going to have 11 like that. Then immediately that happens, the memory data register needs to record that particular content, which is just a 3. So in the memory data register, you have a 3 like that. Then once that happens, this 3 now needs to be passed to the current instruction register. Then you have your 3 there. Then now that you have your 3, it is now placed where? Into the accumulator. So the accumulator is going to change. It will have the 3, and remember, the 3 goes via the current instruction register, the control unit, to make sense of it, and it is now placed in the accumulator. So you have your 3 here. So remember, the 2 which was initially in the accumulator has already been passed to the arithmetic logic unit. And before that, the first thing which was passed is an add instruction. So the accumulator knows that whatever is going to come from the, the arithmetic logic unit knows that whatever is going to come from the accumulator, I'm going to add it to whatever is already here. If you would have said subtracted, multiply, the arithmetic logic unit would have known that. So now this 3 is now passed to the arithmetic logic unit. So it comes in here and then an add operation occurs. So you have something like the 2 which was initially there plus 3, right? And then in the end, what you have is the result. So the arithmetic logic unit initially gives you the result. And then immediately that happens, this 5 is now stored back into the, not necessarily stored, but it goes back into the accumulator. So that now you have an accumulator because it is keeping a running total. Hence the name accumulator. It's accumulating, so that if there was another instruction, you could have added it there, but it's accumulating. Then it happens like that. So now, once this process has been done, which is now the process we are calling executing, it's like we have done the second instruction. Remember, the program counter at this point is already pointing to the next instruction to be fetched. So at this stage, the memory address of the next instruction 102, which is stored in the program counter because it's always pointing to the next instruction, is going to be just copied in the memory address register. So in the memory address register, you have 102. Immediately that happens, the content of that memory address 102 is loaded in the memory data register. So in the memory data register, you are now going to have that instruction, which is store 12. Remember, down here, these numbers are representing the addresses and not necessarily the specific numbers 12. So store 12 is now going to be passed to the current instruction register. So what you're going to have in the current instruction register is store 12. Makes sense? So now remember, what this means is go to the accumulator, get what is in the accumulator and store it in the memory address 12. And initially in that memory address there is nothing. This is what the 0 means. There is initially nothing. So again, this instruction is going to be passed. It goes to the control unit. The control unit is going to make sense of it, and that's the process we're calling decoding, because the instruction has been fetched. It is now going to be decoded in the control unit. Once the control unit makes sense of it, hence comes now the process execution. So to execute now, it needs to get what's in here and store it in the memory address 12. Make sense? Yes. So this content moves via the control unit. It goes and it passes like that. So once it's passing like that, remember what we're doing is we want to put something into the location 12, and this is in the RAM. So it's like we want to put something into the RAM. So first and foremost, remember the first thing that happens is that memory address needs to be copied into the memory address register whenever we're putting something in the RAM or we're getting something in the RAM. So what's that memory address? It is 12. So this 12 is going to be copied into the memory address register. So here you're going to have 12. Make sense? So once that memory address has been copied, now we want to put something into that memory address. It's like we're not getting, but now. So what's going to happen is the content of the accumulator move via the memory data register. So it's like the content which was initially in the accumulator, because initially what would have happened is if we were getting something from the memory address 12, it would have moved and it would have been stored into the memory data register and back to the current instruction register, but it's like the opposite. Current instruction register, and it now goes to the memory data register, and then you'll find that the result which is in the accumulator will be stored in the memory location 12. So what's the result? 5. So in here what you're going to have is a 5. So that way the instruction which we initially had, which was add 10, load 10, add 11 and store 12, has been completed. Yeah, so this is a classical example of how a program is executed and how the program counter comes into play. So as you can see, it's not very easy to explain the program counter on its own. We have to bring on board a lot of other concepts. Yeah, but that's the main idea there of what happens. Hopefully you guys enjoyed this video, and like I always say, be sure to hit that like button and subscribe to my channel. It will really mean a lot, and that way you won't miss any future videos which we're going to upload here. And then if you want to be part of our team, want to get personalized tutoring just specifically for you and get access to our materials, be sure to join us. I'll leave my details in the comment sections. You guys can text me on WhatsApp and the likes. Yeah, so in the next video we're going to look at the last part of chapter 1. Then we'll look at some practice questions from the exam. Then we should be good to go to chapter 2. So I'm going to end the video here, and I thank you guys.